Findings of the Sciences. Chapter 4, Principia Mathematicae, Mathematical Analysis. The great development of mathematics in the 19th century was an essential part of the development of the natural sciences, especially mechanics and physics, and the way from 19th century positivism to its successor philosophies in the 20th century goes through the discoveries of mathematics and mathematical logic. Mathematics is written down and elaborated as a system of definitions and theorems concerning spatial elements and numbers, so that it looks as if it could ideally be worked out in its entirety independent of every other technical accomplishment or scientific investigation. Just as there is controversy about the subject matter of the empirical sciences, so there is controversy about the subject matter of mathematics. What is it all about? Way back at the beginnings of Western philosophy, the Pythagoreans and Platonists were engrossed with problems about the nature of mathematics, and put forward the view that it brings knowledge of pure forms or ideas which are self-subsisting and eternal, and are, somehow or other, materialized in the world of sense. This view had a considerable appeal for some of the modern philosophers of mathematics too. However, if we consider how mathematical theory actually develops and how it is used, it becomes pretty evident that people do not make discoveries about space and number until they are practically engaged in measuring and counting, and that the concepts of pure spatial forms and of numbers are reached by a process of abstraction from comparing, measuring, counting and dividing material objects. Mathematical theory develops along with technology and the associated empirical sciences, and serves the purpose of providing techniques for stating quantitative relations within material processes, and making calculations about them. The differential and integral calculus, as first formulated by Newton and Leibniz, was a mathematical technique devised for use in mechanics, for calculations concerning mechanical motions, as well as for the solution of analogous geometrical problems. For example, if a body is accelerating under the influence of forces continuously acting on it, that means that from instant to instant its velocity is increasing. How to calculate its velocity at an instant, and the increase from instant to instant. The calculus was devised to solve this kind of problem. For this purpose it treated of infinitely small increments occurring in infinitely short periods of time, the ratios of infinitely small quantities, and the summation of such infinitesimals. Originally formulated in such terms, it did yield the practical results required of it, but it lacked rigorous definitions of its terms and proofs of its theorems, so that it was impossible to see just how the results were arrived at. In this respect it was an efficient but still imperfect instrument, and as mechanical and physical science and technology advanced, a better constructed mathematical tool was required than Newton and Leibniz had provided. This led to the later and very brilliant development of mathematical analysis. Some credit is due here to the philosopher George Berkeley, who as early as 1734 attacked the fundamental concepts of mathematical analysis, as they were then formulated, in a pamphlet called The Analyst, or a discourse addressed to an infidel mathematician. As usual, Berkeley was chasing infidels, and his aim was to examine whether the object, principles, and inferences of the modern analysis are more distinctly conceived, or more evidently deduced, than religious mysteries and points of faith. He concluded that they were not, and that mathematicians should clear up their own mysteries before they presumed to question those of the theologians. The first part of this advice was well-founded, and mathematicians did take it about a century later. Berkeley drew attention to the fact that the concept of the infinitesimal was undefined. Now to conceive a quantity infinitely small is, I confess, above my capacity. But to conceive a part of such infinitely small quantity that shall be infinitely less than it, is, I suspect, an infinite difficulty to any man whatsoever, and will be allowed such by those who candidly say what they think, provided they really think and reflect, and do not take things upon trust. And he also drew attention to the consutidiectiveness of the proofs of the calculus. If the theorems nervurdialis worked, he said, they must be based on other principles than those alleged by their authors. When the conclusion is evident and the premises obscure, or the conclusion accurate and the premises inaccurate, we may safely pronounce that such conclusion is neither evident nor accurate, in virtue of those obscure inaccurate premises or principles, but in virtue of some other principles, which the demonstrator himself never knew or thought of. These other principles, which Berkeley demanded, were worked out by the great mathematicians of the 19th century, who introduced exact definition and rigorous proof into mathematical theory. The rigorous proof of theorems in mathematics depends on exact definitions. The procedure of analysis involved, first, taking certain terms and relations between them as primitive or undefined, such as points, lines and planes, in plane geometry, or, in arithmetic, 0 and the operation +1, leading to the series of natural numbers. Second, formulating axioms concerning the terms and their relations. The axioms must be independent and consistent, i.e., no axiom may follow from or be incompatible with the others. Third, defining other terms and other relations so as to show their construction from the primitive terms and relations. That being done, theorems can be proved from the axioms and definitions. This analytic procedure was very successful indeed in the theory of numbers. Calculation and reckoning, as required in geometry and mechanics, operates with various different sorts or types of numbers. To begin with, there are the whole numbers, or cardinal numbers, o, I, 2, 3, n, and I1. These are used for counting, and may be added and subtracted, multiplied and divided. If you subtract a number greater than itself, the result is a negative number. For example, 2, 3 equals, I for reckoning relations and proportions, what are called fractions, ratios or rational numbers are used. Then, however, complications turn up in the form of the so-called irrational numbers. Thus there is no rational number equal to the square root of 2, or equal to the ratio between the circumference and the diameter of a circle, denoted by the Greek letter tc. However, Va7c and other irrational numbers are needed for calculation, so these irrational numbers have to be used along with the rational numbers, the whole lot together being called real numbers. And then further complications arise, involving so-called imaginary numbers. Since the multiplication of a negative by a negative is always positive, it follows that there can be no real number equal to the square root of a negative number. However, for some purposes of calculation, multiplication by the square root of -1 is required. Such a number is called imaginary, because no real number can possess such a property. A basic achievement of analysis was, then, the definition of all these various kinds or types of numbers in terms of the cardinal numbers, using for this purpose only the concepts of order, set, or class, and limit. Starting from the natural numbers, positive and negative cardinals were defined, and then rational numbers were defined as ordered pairs of cardinal numbers. If, then, the rational numbers are considered in order of magnitude, it can be shown that any rational number divides them into two sets, such that it is the upper limit of the one set and the lower limit of the other. For instance, the rational number is the upper limit of the rational numbers less than if they are considered in ascending order of magnitude, and the lower limit of those greater than ji, considered in descending order of magnitude. This simple consideration provided the clue for defining irrational numbers. If you consider, for example, the set of rational numbers less than v2, and the set greater than vj, there is no rational number which is the upper limit of the one and the lower limit of the other. In this way, what Dedekind called gaps appear in the series of rational numbers, corresponding to the irrationals, and this circumstance was used to define irrational numbers themselves. The irrational numbers corresponding to the gaps could be defined as the sets of rational numbers below the gap. Thus, for example, y is the set of rational numbers in order of magnitude the squares of which approach nearer and nearer to 2 without ever equaling 2. The real numbers could then all be defined as ordered sets of rational numbers, and were divided into rational real numbers and irrational ones, according as they had or had not a rational number as upper limit. Having got so far, the theory of the junctions of a real variable was worked out. An expression x equals phi is called a function of a real variable when the variables n y take real numbers as their values, and when expresses a rule whereby to every value of y there is assigned a corresponding value of I. It is then possible to define functions such that when y varies continuously towards a defined limit, so does x, and these definitions then permitted all the theorems of the old calculus, and a lot more besides, to be rigorously formulated and proved, in terms of functions of real variables, without any recourse to such obscure concepts as infinitesimal quantity. Further successes for analysis were scored when it was shown that the so-called imaginary numbers could be defined as ordered pairs of real numbers. In this way, theorems concerning the imaginaries could be as rigorously proved as any others, and the principles of calculation with imaginaries were put on a firm basis. The imaginary numbers were renamed complex numbers, and a very high degree of generality in the formulation of mathematical theory was achieved in the theory of the functions of a complex variable. Subsequently, other operations have been defined, such as those employing matrices, introduced into calculations of quantum physics, which do not obey the commutative rule, i.e. AB is not equal to 2. Mathematics and logic. The success of mathematical analysis suggested that something of the sort should be done for the theory of formal logic, the aim of which was to formulate the general principles employed in reasoning, i.e. in deducing one proposition from another. The foundations of formal logic had been established for more than 2,000 years by Aristotle, whose greatest achievement was the technical one of introducing a notation using variables. Since Aristotle, it has been taken for granted that general formulas should be expressed by the use of letters, or other symbols employed as variables, and that meaningful expressions to which these formulas apply should be obtained from them by substituting meaningful symbols for the variables. Thus Aristotle's formula for the syllogism, employing the variable terms a and b, if all a is b, and all b is c, then all a is c, all jives a rule of inference applicable when meaningful terms are substituted for the variables. For example, if all men are mortal, and all Greeks are men, then all Greeks are mortal. The subsequent development of mathematics and of mechanics would not have been possible without a notation employing variables, as first demonstrated in Aristotle's Analytics. Although Aristotle has been much decried, the sciences owe him a great deal. However, while mathematics forged ahead, formal logic remained in a very imperfect condition. Its chief defect was that in its formulas the same variables, a, b, etc., were used indifferently to stand for individuals, properties of individuals, and classes, and that no formulas at all had been devised for expressing relations. As a consequence, the traditional logical theory lacked formal rigor, CAP-WM virtually inapplicable to the processes of reasoning involved in the modern sciences. The starting point for the reformulation of formal logical theory was made in Die Algebra of Logic worked out by Boole and others in the middle of the 19th century. Boole used a notation in which all the variables stood for classes, a class being to consist of all the individuals possessing some common property, and by this restriction he was able to construct a system of all applicable to classes and the relations of classes, which could be rigorously proved. Then De Morgan, Peirce and others extended to the general logical theory of relations. The key contribution to the advance of logical theory was made by Frege in the last quarter of the century. Frege's aim was not, however, to present logic as a branch of mathematics by working out an algebra of logic. He rather saw mathematics as a continuation of logic. What he set out to do was to take the definition of number a stage further back, by defining cardinal number in terms of the non-mathematical and purely logical conception of class. Cardinal numbers express the results of counting, and are used for saying how many members belong to a given class. A cardinal number is always the number of a class. Classes have the same number of members when to each member of the one there corresponds a number of the other, and classes between which there exists such a one-to-one correlation may be called similar. It is, then, possible to define classes of similar classes, which all have the same number of members. What Frege did was to define cardinal numbers as classes of similar classes. In terms of this definition, a series of cardinal numbers, from 0, the number of the null class, onwards, could be defined, and the operations of addition, subtraction, multiplication and division could be defined so as to give all the right answers. 2 plus 2 was proved equal to 4. This method of defining cardinal number meant mathematics should be derived from logic, but to carry out AIS derivation evidently required a reformulation of the principles of logic. An analysis was required which would deduce the recognized principles or theorems of formal logic from a minimum set of axioms, and do so in such a way that there could be constructed from it the definitions required to pass from such logical concepts as class in relation to the mathematical concepts of number and quantity. Frege himself employed for this purpose a clumsy and very complicated notation, which was a barrier to the development of his program. Others, however, invented a more workable notation, and these efforts culminated in the production of Principia Mathematica by Bertrand Russell and A. N. Whitehead. 3. The system of Principia Mathematica Cap and Principia Mathematica, the basic conception, taken as primitive, i.e. as self-understood and not to be defined in terms of anything else, that of the elementary or atomic proposition. Such a proposition, which says that a certain individual has a certain property, or that certain individuals are related by a certain relation, is the simplest possible form of statement. Such propositions are analyzable into simpler propositions, but from them, on the other hand, all other forms of proposition can be derived. Denoting elementary propositions by the letters P, Q, it was shown that from every elementary proposition, P can be constructed its negation, not P, and that from elementary propositions and their negations can be constructed molecular propositions. Principia Mathematica took as the basic, or undefined, operation for constructing molecular propositions the operation commonly expressed by the word or, P or Q, implies, or if, then, was defined in terms of or, P implies Q means, by definition, not P or Q. For example, if you move I will shoot you was represented as meaning the same as don't move or I shoot, which quite accords with common usage. The most important logical device of Principia Mathematica was that employed for the construction of general propositions, i.e. propositions which refer, not to specified individuals, but to all or some unspecified individuals which possess some common property or stand in some relation. This involved the introduction of what were called propositional functions, and operational symbols called quantifiers, which applied to propositional functions. Propositional functions and their quantifiers were due to Frege, and represented his most important and abiding contribution to formal logical theory. A propositional function was defined as an expression containing a variable, such that, when a value is given to that variable, the result is a proposition. Thus where f and g stand for properties belonging to individuals, the expressions fx, gx, are elementary propositional functions, and elementary propositions are obtained from them when the variable x is replaced by references to specific individuals. Thus, for example, x is read as a propositional function, which has as values this is read, that is read, etc. Suppose, then, we construct a compound propositional function fx, implies gx, dot. A general proposition may be obtained from this by saying, that this function yields true propositions for every value of x, or, 2, that it yields true propositions for some values of x. The first operation was represented symbolically as follows, x, fx, implies gx, which, in ordinary language, may be read as for every x, fx, implies gx, dot. The second operation was represented by, 2, 3 times, fx, implies gx, which, in ordinary language, may be read as for some x's fx, implies gx, or, what comes to the same thing, there is an x, such that fx, implies gx, dot. The operational signs, x, and 3 used for these purposes are known as quantifiers, and the operation is known as the quantification of a propositional function. All general propositions could then be represented as constructed by the quantification of propositional functions. Though it looks difficult when first encountered, this technique achieved an extraordinary simplification and clarification of traditional logical theory. It enables all the principles of logic, whereby one proposition is validly inferable from another, to be exactly formulated and rigorously proved. Formal logic became an exact calculus. The principal use made of quantification technique in Principia Mathematica was for the analysis of propositions about classes. Consider, for example, a proposition class A is included in class B, say, the class of all Frenchmen is included in the class of all Europeans. This looks like a proposition asserting a relation between certain entities, namely, classes, and that is how it had been treated in Boole's algebra of logic. However, a class is defined as consisting of all the individuals possessing a certain property. Let F be the defining property of class 4, and G of class B. Then the proposition class A is included in class BK, by FHE quantification technique, be represented as saying, xfx, implies gx, dot. In a verbal example, the class of all Frenchmen is included in the class of all Europeans simply says, for every x, x is French implies x is European, or still more simply, everyone who is French is European. Thus by means of the quantification technique, propositions about classes could be constructed from propositions about individuals, and there was shown to be no need to postulate such entities as classes existing additionally to the individuals which are the members of classes. The authors of Principia Mathematica expressed this by saying that classes are incomplete symbols or logical constructions, which disappear in analysis. An important application of this technique of analysis was made in what was called the theory of descriptions, as well as such class expressions as the class of all Frenchmen. Such descriptive expressions as the present King of France had occasioned much debate amongst logicians and philosophers. The expression the present King of France looks as if it stands for some object, namely, the present King of France. But since France is a republic, what is this object, and where is it to be found? And if the expression does not stand for anything, how can it have any meaning? Some philosophers went so far as to say that the present King of France enjoys an immaterial existence in the realm of ideas, even though deprived of material existence in France. However, by means of the quantification technique, a very simple and convincing analysis was offered of propositions containing such descriptive phrases. Suppose, for example, that it is asserted that the present King of France is bald. This simply says, there is an individual, such that he is at present King of France and he is bald. Since there is in fact no such individual, the proposition is false, but there is no real puzzle as to the reference of the descriptive phrase. Such expressions as the so-and-so are, like the class of so-and-so, incomplete symbols which disappear in analysis. To get from here to the definition of cardinal number required a series of further operations employing quantification technique. First, relations were dealt with, so that statements of the similarity and dissimilarity of classes could be constructed. Similar classes have the same cardinal number, and so propositions about cardinal number, the elementary propositions of arithmetic, could be constructed as propositions about similar classes, and these in turn were constructed as more complicated statements about the one-to-one correlation of individual members of such classes. Cardinal numbers were thus defined, following Frege, as classes of classes. To say something about the number 2, for example, is to say something about all classes with 2 members, but classes of classes, like classes, were shown to be incomplete symbols disappearing in analysis. These constructions, as might be expected, turned out very complicated indeed. In particular, they were found to involve what in Principia Mathematica was called the theory of logical types. Individuals, classes, classes of classes, etc., are of different logic types, and rules had to be formulated to forbid confusion of types. However, axioms and definitions were worked out so that the arithmetical properties of cardinal numbers could be deduced from the logic of classes and relations. For the flaws in the system, how successful was Principia Mathematic's deduction of mathematics from logic? Could the claim that this had been achieved be substantiated? Further examination of the system has revealed flaws in it, and 2 in particular which show that the conceptions employed need some drastic revision. Apart from some technical difficulties connected with the theory of types, the first objection concerns the method of defining cardinal numbers. A number was taken to be the class of all classes with members, and the definition supposed that there actually exist as many as n individuals, otherwise there would be no classes with n members. Hence to define, as was required, an infinite series of cardinal numbers, in which every number is followed by the number 1 greater, and so on without end, there had to be introduced a special, and quite arbitrary, axiom, the so-called axiom of infinity, which says that for any number, however great, there exist at least that number of individuals. This axiom made the whole system of mathematical truths, supposedly independent of any matter of fact, dependent on an alleged matter of fact, namely, that the number of existing individuals is infinite. Thus Principia Mathematica postulated that an infinite number of individuals exist, and from this was deduced the existence of an infinite series of cardinal numbers, and an even greater number, of a higher order of infinity of real and complex numbers. It was thus a system for deducing necessary truths, expressing formal properties of propositions, of classes, and of numbers, consequent upon the existence of an infinite number of individuals. But that the existence of an infinity of individuals is a necessary truth is far from evident. How can this be known? Indeed, what precisely does it mean? That for every cardinal number there is a rule for constructing a number 1 greater, so that there is no greatest cardinal number, and so that however many individuals may be counted the numerical system always provides for counting some more, is undoubtedly a necessary truth. But in Principia Mathematica this necessary truth was made dependent on a postulate of empirical fact, which cannot be deduced from any purely logical considerations, and which can never be verified empirically either. Such a postulate, put forward as an axiom, is quite arbitrary in relation to the construction of a working logical mathematical calculus, but without it, the calculus would not yield the results required. The second objection is even graver, and more decisive. It arose out of problems presented by so-called improvable theorems in mathematics, and it, too, is concerned, in another way, with infinity. There is an infinite series of numbers, and no limit to the theorems which, theoretically, may or may not be true of them. Is it, then, possible to establish a set of axioms such that it can be proved that all true theorems about numbers follow from them, i.e. that they enable it to be decided whether or not any proposed theorem is true? Mathematicians have been able to formulate theorems about numbers, which are true of all numbers that anyone has ever calculated with, but which they have found themselves quite unable to prove. An example is the theorem that every even number is the sum of two primes. Take any even number you can think of, and this theorem is true of it. Thus 2 equals AFI, 4 equals 3FI, 6 equals 5TI, 8 equals 5 1/3, IO equals 7 plus 3 inches 12 equals 7F5, and so on. But no one has succeeded in proving that being the sum of two primes is necessarily true of every even number in the entire infinite series of even numbers. Now, of course, it cannot be proved that any given theorem is unprovable. All that can be said is that a given theorem has defied all efforts to prove it, and so it might still have been hoped that one day any unproved theorem would be proved, so that everything connected with number would be provable and its eternal necessity demonstrated. Had it not happened that the opposite was proved in a paper by Kurt Gödel, published in 1931, on formally undecidable propositions of Principia Mathematica and related systems. With great technical ingenuity, Gödel furnished a proof that no set of axioms can ever be capable of deciding or proving all theorems about numbers. It is important to be clear as to just what Gödel did and did not establish. Gödel's proof did not impugn the axioms, definitions and theorems of Principia Mathematica, though the objection remains that the theorems would not follow without the arbitrary axiom of infinity. It certainly did not demonstrate, as some enthusiasts for unreason have tried to make out, that logic and mathematics provide only fallible instruments of human calculation, and that reason must always break it down. Rather, it demonstrated that no technical development of logic and mathematics can ever represent the final end, the ultimate achievement of universality and formal perfection. There is no system of necessary truth such that we have only to discover the foundation principles, and all of it without end comes within our grasp. Briefly, these two objections, or major difficulties involved in the working out of the system of Principia Mathematica, add up to the following. First, while formally numbers exhibit the properties of classes, the definition of cardinal numbers in terms of classes does not enable arithmetic, and then the rest of mathematics, to be deduced from formal logic. For with mathematics, there enters the definition and deduction of the properties of infinite aggregates and infinite series, which cannot be derived from the elementary logic of propositions and classes. Second, no set of primitive concepts and axioms is feasible by means of which all questions of the properties of numbers and the results of mathematical operations could be decided. The development of mathematics must therefore be like that of the empirical sciences which mathematics serves, in the sense of being an endless quest of technical invention and discovery. It does not consist of the unfolding of the formal consequences of any set of necessary principles established and finalized once and for all. That is what these objections add up to. And so, of course, they do not invalidate the elementary calculus of propositions, or the quantification technique and its applications, or the logical theory of classes and relations, or the foundations of arithmetic, or definitions of real and complex numbers, or the theories of the functions of real and complex variables, or any other of the great technical achievements of modern logic and mathematics. But what they do show is that the idea of demonstrating the principles of logic and mathematics as a self-contained system of necessary truth deducible from axioms of formal logic is one which necessarily cannot succeed, and that the conceptions employed in Principia Mathematica therefore need revision. 5. The interpretation of logical and mathematical analysis. When people achieve something, they often misunderstand it and represent it as other than it is. To do something, and to know just what you are doing, are not the same thing. In some aspects, philosophy, as a critical reflection on nature and human life, is a product of this circumstance. It is an effort to get to know what we are doing, and its value and practical importance stem from this. For it is not enough just to do something, we need to know what we are doing, or what we do is apt to land us in difficulties we did not expect. The achievements of logical and mathematical analysis were impressive, but Frege, and afterwards Russell, worked with a conception of what analysis does which led to difficulties. The conception of analysis due to Frege, and developed in Principia Mathematica, represented analysis as the reformulation of propositions in such a way as to make explicit exactly what they refer to. Thus Frege's definition of cardinal number was represented as demonstrating that the objects which mathematical propositions about cardinal number refer to are classes of classes. The Principia Mathematical theory of incomplete symbols and logical constructions was a generalized theory about how such analysis is done. Thus the analysis of objects, A, was to be accomplished by reformulating propositions phi, in the form gx, y, z, where x, y, z, are the objects referred to in propositions nominally about A. The sign A was thus shown to be an incomplete symbol, and A was shown to be a logical construction out of the elements x, y, z. Such analysis could, then, be carried on until it arrived at the ultimate or irreducible elements to which propositions nominally about other things refer. All these other things were then revealed by analysis as logical constructions out of the ultimate unanalyzable elements. From this it was rather rashly concluded by Russell that logical analysis had at last revealed what philosophers had often wanted to know, the ultimate structure of reality. The simplest form of proposition, the atomic proposition of Principia Mathematica, referred to the ultimate unanalyzable elements of reality, atomic individuals, with their simple qualities and relations. The fact expressed by an atomic proposition, namely, that a certain individual has a certain property, or that certain individuals stand in a certain relation, was called an atomic fact, and the real world was revealed by analysis as a kind of granular structure of atomic facts. This conclusion was given the name logical atomism. This conclusion by itself is enough to make suspect the conception of analysis from which it was derived. For it seems extraordinary that a definitive conclusion about the metaphysical structure of the universe should be deducible from the discovery of a technique for making a logical calculus. That atomic or elementary propositions, which say what properties individual things have or how they are related, are the simplest kind of propositions that can be constructed, and that more complex forms are to be derived from these elementary forms, as demonstrated in Principia Mathematica, is, indeed, indubitable. But it simply does not follow from this that the world consists of atomic facts. That such a statement as this is read is the simplest sort of statement does not entail that such simple statements must refer to unanalyzable individuals with their unanalyzable qualities and relations. For the fact is that statements such as these, though formally simple, are at the same time extremely abstract. If, then, one wishes to say more concretely what is the case, one has always to make more complex and generalized statements. For the individual things about which we make statements are never simple, ultimate or unanalyzable. If I point to something and say this is red, which is logically the simplest form of statement I can make, I am not thereby getting down to metaphysical bedrock and stating a simple and irreducible atomic fact. On the contrary, my statement is very abstract, and the more I try to say what exactly is the case which renders my statement a true one, the more complicated in logical form will my statements become. That in logical analysis more complex statements are constructed out of simpler ones does not demonstrate, therefore, that the simplest statements reveal the irreducible elements to which the more complex ones refer. For the logical analysis of how statements are to be constructed is not at all the same thing as an analysis of the objects to which the statements refer. However, it was precisely on the assumption that analysis consists of the revelation of what statements refer to, that the achievements of analysis in logic and mathematics were interpreted. They were interpreted as demonstrating that propositions about complex numbers refer to real numbers, about red numbers to rational numbers, about ration numbers to cardinal numbers, about cardinal numbers to classes, and that propositions about classes refer, finally, to the irreducible individuals which are members of first-order classes. with their irreducible quantities and relations by virtue of which they are classified. 6. Logical and mathematical necessity. Now obviously, the propositions of logic and mathematics differ from commonplace fact statements and from the generalizations of the empiric sciences, inasmuch as their truth is necessary and demonstrable. The concept of antithesis had, therefore, to explain and make manifest the distinction, stressed earlier by Hume, between knowledge of matter of fact and of necessity, or between what is conjecture based on observation and what is self-evidently necessary or can be formally proved, and this it proceeded to do in terms of the distinction between the content or meaning, and the form, of propositions. Thus, for example, the propositions "this is red and that is green" differ in meaning but are identical in form. Propositions, whether singular or general, which state that certain things have certain quantities or stand in certain relations, are true or false, but we cannot tell whether they are true or false simply from their analysis. Their truth or falsity depends on whether what they state is a fact or not, and this we can only get to know, if we can know it at all, by observation of facts. We cannot discover independently of observation whether such propositions are true or false. All the propositions asserted by empiric sciences are of this kind. On the other hand, so the theory continued, logic, and likewise mathematics, are concerned purely with form, and it is for this reason that the propositions of logic and mathematics express necessary truths. Their necessary truth is made manifest by analysis. A proposition of logic, Russell explained, is absolutely general. It applies to all things and all properties. As an example, he cited the proposition, if anything has a certain property, and whatever has this property has a certain other property, then the thing in question has the other property. Such a proposition is purely formal, since it does not mention any particular thing, or even any particular quality or relation. It is wholly independent of the accidental facts of the existent world, and can be known, theoretically, without any experience of particular things or their qualities and relations. He went on to say that in the formal calculus of logic, there are formulated supremely general propositions, which assert the truth of all propositions of certain forms, and this merges into pure mathematics, whose propositions all turn out, on analysis, to be such general formal truths. Thus logic and mathematics consist of formal or absolutely, or supremely general truths, which can be known independently of all particular experience, and are necessarily true. Since such necessary truths are true by virtue of their form, their truth can always be made evident by formal analysis, starting from primitive or self-evident formal truths, and using methods of formal construction and proof to build up from that basis. Thus, starting with formal generalizations of elementary logic, like the one cited above, which are the simplest of formal generalizations, we can proceed to the logical construction of more and more complicated generalizations, expressed not in terms of any individual, but of any class, any relation, any class of classes, and so on. And in this way, starting from elementary logic, we may construct and prove the whole of mathematics. 7. The object of analysis, the program of Principia Mathematica, for deducing mathematics from logic, thus followed from the conception of analysis. Conversely, the success of the program would demonstrate the soundness of the conception of analysis on which it was based. But as we have seen, in the end the program turned out not to be an unqualified success after all. In the first place, mathematics could not be made to follow from logic without introducing the axiom of infinity, which is certainly not an absolutely general formal truth of the sort required. In the second plaque, Gödel's proof proved that theorems of mathematics, which according 65, the program ought to be absolutely general and formal propositions, the necessary truth of which can be proved and made manifest by analysis, are not all capable of formal proof. This outcome of the program is quite fatal to the whole conception of analysis which inspired it. So a negative conclusion about the stated conception of analysis seems inescapable. Whatever the analysis undertaken in modern logic and mathematics does, and there can be no doubt at all that it does do something, and does represent a technique capable of producing undeniable results, it does not proceed by revealing exactly what all propositions refer to. The conception of analysis as doing that leads, on the other hand, to the arbitrary metaphysical conclusions of logical atomism, which are empirically unverifiable and formally uncertifiable, and, on the other hand, to a program for deducing mathematics from logic which will not work. The view, Associated with this conception of analysis, that logic and mathematics consist of formal and supremely general truths, led Russell to a combination of logical atomism with a version of Platonic idealism. In an essay on the study of mathematics, contained in his book Mysticism and Logic, he wrote, "Philosophers have commonly held that the laws of logic, which underlie mathematics, are laws of thought, laws regulating the operations of our minds. By this opinion the true dignity of reason is very greatly lowered, it ceases to be an investigation into the very hard and immutable essence of things actual and possible, becoming, instead, an inquiry into something more or less human and subject to our limitations. But mathematics takes us still further from what is human, into the region of absolute necessity, to which not only the actual world, but every possible world, must conform, and here," he went on, "it finds a habitation eternally standing. It is only when we understand the entire independence of ourselves, which belongs to this world, that reason finds that we can adequately realize the profound importance of its beauty. It is this view that logical and mathematical analysis are not concerned with anything human and subject to our limitations, but discover formal truths eternally standing in entire independence of ourselves, which the actual development and uses of analysis compel us to question. Logic and mathematics are concerned with operations involved in human statement, reasoning, counting and measuring, locating things in space and time and specifying their motions. These are the objects of their analysis. The distinction between logical and mathematical procedures, the analysis of which demonstrates the necessity attaching to their results, and what Hume called reasonings from causation and concerning matters of fact, in which, as he said, this absolute necessity cannot take place, is not to be questioned. But what is to be questioned is that what logic and mathematics demonstrate are supremely general propositions, stating the immutable essence of things actual and possible. What are called propositions of logic and mathematics are not propositions at all, in the sense of the word applicable to observational statements and to the hypotheses of empirical science. They are not propositions true of all things without qualification, as distinguished from propositions of empirical science, which are true of particular classes of things having particular properties. The distinction between what is matter of fact and what is logically or mathematically necessary is not one between general propositions, which require empirical verification, and absolutely general propositions which are certified by virtue of their form alone. The distinction lies rather between the conclusions of investigating things, conclusions which require to be empirically verified, and for the derivation and formulation of which techniques of reasoning and calculation are used, and the elaboration and certification, for use in such investigations, of those techniques themselves. 8. Analysis and philosophy, the employment of methods of analysis, first to construct rigorous proofs in mathematics, and then to reformulate principles of formal logic, suggested to some philosophers, and to Bertrand Russell in particular, that the same methods could be extended to philosophy. Could not philosophy be made analytic, on the model of mathematics and logic, so that the dubious and often ambiguous generalizations of philosophy should be replaced by the exact analysis of concepts, demonstrating with clarity and precision their true and indubitable foundation? The fact that Russell, co-author of Principia Mathematical, was the principal founder of the analytic philosophy, has led to the belief that this philosophy, along with the 19th century positivism which it in fact continued, was what inspired and was responsible for the successes of analysis in formal logic and mathematics. Those successes are therefore cited as evidence in philosophy. This is not, however, the first time that philosophy has tried to imitate and model itself upon the methods of the exact sciences. Descartes thought that the methods which had served him so well in geometry should provide the model for philosophy. We do not therefore conclude that his philosophy had the merit of inspiring discoveries in geometry, but rather that he had misunderstood the methods of geometry in supposing them to be applicable in philosophy. The introduction in the 19th century of exact definition and rigorous proof into mathematics, and then into formal logic, was primarily the result of needing more effective logical and mathematical techniques for the purposes of science. The introduction of these methods was not a consequence of any particular philosophical doctrine, and was not inspired by any particular philosophy. On the other hand, it inspired some philosophers with the desire to introduce comparable standards of precision and rigor into philosophy. We have already seen that a misunderstanding existed as to the nature of logical and mathematical analysis. It was only on the basis of this misunderstanding that the application of these methods to philosophy was proposed. The proposal was, in the circumstances, a natural one enough, for positivist philosophers were already describing the methods they employed for interpreting the findings of the sciences as analytic. These findings were interpreted and substantiated by making them out to consist of statements of laws regulating the combination and sequence of sensations, and this, the philosophers claimed, was an antithesis of the main concepts used in science. Thus Mach, for example, claimed to have shown that bodies, and all the constituents of bodies discovered by scientific research, such as atoms, molecules, cells, tissues, etc., etc., were revealed by his analysis of sensations to consist of sensations. Sensations were the ultimate individual elements to which all knowledge referred, and all propositions about bodies and their elements were, in his analysis, represented as propositions about sensations. This meant, in the terminology of Principia Mathematica, that external material things, and the same would go, as Mach also suggested, for minds, were incomplete symbols, which disappear in analysis, the corresponding objects being thereby shown to be logical constructions out of the elements of sensation. The proposal to extend the application of analytic methods from logic and mathematics to philosophy was, then, a proposal whereby positivist philosophers could state their ideas rather more systematically, and in a new terminology. It meant that the questions philosophers asked were to be posed in a new way. Instead of asking questions like how do we gain knowledge, what do we know, or do external material things exist independent of being perceived, all questions were to be put in the form, what is the analysis of such and such propositions? The introduction of what was supposed to be the tried method of logical mathematical analysis into philosophy was widely advertised as affecting the regeneration of philosophy. It did give positivism a new lease of life, and enable it to develop its doctrines in some new ways to meet new circumstances in the 20th century. But it soon led to greater difficulties than any it could claim to have solved, and it is out of these difficulties that the linguistic philosophy eventually emerged. Chapter 5, Loose Search of the Right Analysis or Knowledge of the External World, proclaiming the logic